This is Spacetime, Series 23, Episode 56, for broadcast on the 8th of June, 2020. Coming up on Spacetime, confirmation of a second planet orbiting Proxima Centauri, discovering the universe's missing matter, and a new type of matter inside neutron stars. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
Astronomers have discovered a second exoplanet orbiting around Proxima Centauri, the nearest star to Earth other than the Sun. Proxima Centauri is a spectral type M red dwarf star, located approximately 4.25 light-years away. It's part of the Alpha Centauri triple star system, which comprises the two primary stars Alpha Centauri A and B, which orbit each other, and Proxima Centauri, which orbits the pair. Alpha Centauri is easily seen with the unaided eye from Earth, at least in the southern hemisphere. It's the more distant of the two pointer stars, showing the way to the Southern Cross. The new planet, provisionally named Proxima C, has about 7 times the mass of the Earth, with an orbital period of 1,907 Earth days. The study's lead author, Fritz Benedict from McDonald Observatory, used data he originally took over 2 decades ago, using the Hubble Space Telescope, to confirm the existence of Proxima C and determine its orbit and mass. Back in 2016, astronomers confirmed the existence of an Earth-sized terrestrial planet orbiting around Proxima Centauri, making it the nearest known extrasolar or exoplanet to Earth. The planet, known as Proxima b, is a super-Earth with about 1.3 times Earth's mass. It orbits Proxima Centauri at an average distance of just 0.05 astronomical units. That's about 7.5 million kilometres, which is well within Proxima Centauri's habitable zone, a region around the star where temperatures would allow liquid water, essential for life as we know it, to pool on a terrestrial planet's surface. Proxima b takes just 11 Earth days to complete one orbit around its host star. That's far closer than Mercury's 88 Earth-day orbit around the Sun. Now, you may recall earlier this year on Spacetime, we reported the work of a team of astronomers led by Mario De Maso from Italy's National Institute for Astrophysics. They had found evidence of a possible second planet orbiting further out in the Proxima Centauri system, using the radial velocity or wobble method, which measures changes in a star's motion across the sky due to the gravitational effect of an orbiting planet. De Maso and colleagues determined that Proxima C orbits its host star every 1,907 Earth days, at a distance of 1.5 astronomical units. By the way, an astronomical unit, well, that's the average distance between the Earth and the Sun, roughly 150 million kilometres, or 8.3 light minutes. De Maso and colleagues admitted the existence of Proxima C, based on their calculations, was still far from certain. And that's where Benedict came into the picture. He decided to revisit his old data on Proxima Centauri from the 1990s, the readings he got with the Hubble Space Telescope. Now, for that study, he had used Hubble's fine guidance sensors. They're normally used to help aim the telescope. But astronomers also routinely used it for astrometry, that is, the precise measurement of the position and motions of celestial bodies. Benedict used it to study Proxima Centauri's radial velocity in the hope of finding an orbiting planet. But he found nothing, missing Proxima b completely and ending the search after 1,000 Earth days. But now, after revisiting the data to check for signs of a planet with a longer orbital period, he did indeed find it right on 1,907 Earth days. Meanwhile, another team of astronomers, led by Raphael Grattan, also from Italy's National Institute for Astrophysics, published some images which looked like it could be a planet, but it could also have been some background noise at several points along its orbit, using the SPHERE instrument at the European Southern Observatory's Very Large Telescope in Chile. Benedict then combined all 3 of these studies, his own Hubble astrometry, De Maso's radial velocity studies, and Grattan's images, to greatly refine the mass of Proxima C, determining it to be about 7 times as massive as the Earth. I guess the important thing about this analysis is that it shows the power of combining several independent methods of studying an exoplanet. Each approach has its own strengths and weaknesses, but when combined, they confirm the existence of Proxima C, and that's a prime example of the scientific method in action. This is Spacetime. Still to come, discovering the universe's missing matter and a new type of matter inside neutron stars. All that and more still to come on Spacetime. Astronomers using mysterious explosions in the distant cosmos, known as fast radio bursts, have solved a decades-old riddle about the universe's missing matter. Until now, astronomers could really only account for about half of all the normal or baryonic matter created in the Big Bang 13.82 billion years ago. Baryonic matter includes things like protons and neutrons, such as those found in the nucleus of atoms, which go on to make stars and planets and asteroids, houses, cars, and even people. Now, this is different from dark matter. That's something separate that's still very elusive and embarrassingly accounts for some 85% of the total matter in the universe. Still, the new findings reported in the journal Nature show that all this missing baryonic matter isn't really missing at all. It's just floating around there in the vastness of interstellar and intergalactic space at an average density of just 1 or 2 atoms for every 100 cubic meters or so of space. The study's lead author, Associate Professor Jean-Pierre Macquart from the Curtin University node of the International Centre for Radio Astronomy Research, says the extremely low densities involved meant trying to find this missing matter with traditional techniques and telescopes was extremely difficult. In fact, astronomers had unsuccessfully searched for this missing matter using some of the world's largest telescopes for almost 30 years. However, the discovery of fast radio bursts have provided astronomers with a new tool in the search for this missing matter. Fast radio bursts are brief millisecond flashes of energy. They suddenly appear and they can come from any direction in the sky. Scientists don't yet know what causes them, but they're thought to involve incredible amounts of energy. Now, just think about this. The entire total energy output of the sun for 80 years released in just a fraction of a second. That's what a fast radio burst is. One of the interesting features of fast radio bursts is that different wavelengths of the radiation coming from them are spread out by this missing baryonic matter, in the same way as wavelengths of sunlight are spread out into a rainbow of colours when passing through a prism. So, by measuring how spread out a fast radio burst is, and knowing how far away it occurred, it would allow scientists to determine just how much baryonic matter existed between the Earth and the source of the fast radio burst. But of course, fast radio bursts are incredibly difficult to study because they're so ephemeral, so very short-lived, and because astronomers don't know when or where to look for them. It's just literally a sudden flash in the darkness of deep space, and then it's gone. An important breakthrough has been the development of the CSIRO's Australia Square Kilometre Array Pathfinder Radio Telescope, ASCAP, which has been able to pinpoint the location of specific fast radio bursts to their host galaxies. ASCAP's part of the Murchison Radio Astronomy Observatory in outback Western Australia. It has both a wide field of view, some 60 times the size of the full moon, and it can image at really high resolutions. And this combination has allowed astronomers to detect fast radio bursts with relative ease, and then pinpoint the location of their host galaxies with incredible precision, even to the point of knowing where within the galaxy they occurred. Knowing how far away the galaxy is provides the final piece in the puzzle. Macquart and colleagues have now used these characteristics to measure the amount of missing baryonic matter between the source of the fast radio burst and the Earth. And once they had measured 6 fast radio bursts, they pretty well had the equivalent of the Hubble-Lemaitre law of galaxies, only for fast radio bursts. By the way, the Hubble-Lemaitre law, well, it simply states that the more distant a galaxy is from us, the faster it's moving away from us. And it's an important rule, or is that ruler, because it underpins all measurements of galaxies at cosmological distances. Macquart says he and his team have now pinned down the relationship between how far away a fast radio burst is and how much the burst is spread out as it travels through the universe because of the amount of missing baryonic matter it passes through.
Well, what we've done actually is to use fast radio bursts as like a cosmological Swiss Army knife. One of the key characteristics of them is that their bursts only last about a millisecond. And that means that they're susceptible to some interesting effects when they travel through the universe. So the radiation all starts off at the same point, the red and the blue wavelengths of the fast radio burst. But as it travels through intergalactic space, they get out of lockstep. That is, the longer wavelengths get delayed a bit more than the shorter wavelengths. This is exactly analogous to what happens when you shine white light through a prism. It breaks up because the red light travels slower than the blue light through the prism, and hence you get the spectrum. It's exactly the same thing here. So when a fast radio burst arrives at our telescope, after its journey of a few billion years, the shorter wavelengths are out of lockstep with the longer by about a second. And exactly how far they're out of lockstep tells us exactly how much matter they've gone through.
How can you use that to determine how much matter there is in the universe?
Well, that's been the key sticking point, because fast radio bursts, this is their dispersion, or the fact that their radiation gets out of lockstep has been a defining characteristic since they were first discovered back in 2007. So we've known they've been going through this intergalactic gas, but we haven't known how much of the matter that they've actually passed through has been due to the intergalactic gas, because they've got to travel through stuff in their own galaxies as well, and they've got to travel through stuff in our own galaxy, the interstellar medium as we call it. And the real sticking point is that people haven't been able to find positions for these things. The Parkes Radio Telescope, which first discovered fast radio bursts, great telescope. It was able to detect these things and figure out a whole bunch of their characteristics. But it's as blind as a bat in the sense that it could only tell you it came from a region about half the size of the moon, which is useless for telling you precisely which galaxy the radiation came from in the first place. And so we've needed to use the Australian SKA Pathfinder. Well, it needed to be built first, and then we've needed to develop all sorts of fancy systems on this to be able to not only detect the fast radio bursts, but to localise them. And the advantage of ASCAP is that it's got 36 antennas spread across the desert floor in the Murchison Shire, and it can act like a telescope that's 6 kilometres across. So when a burst comes in, it's detected by ASCAP. We've got a computer there that sniffs for the signal and says, aha, I found one. Please dump the buffers. So there are these resolution buffers that sit in the electronics of this telescope and allow us to keep the last few seconds of data. And if we find something, it dumps those last few seconds of data. We go and analyse that in the supercomputer, and we can say where that burst went off to 1/36,000th of a degree or thereabouts. And that's sufficient not only to tell you which galaxy in the universe it came from, but where in that galaxy. We go to our optical telescope over in Chile or in Hawaii, a large 8-metre or 10-metre light buckets, and we stare hard at that position until we've identified.
And the Keck you're talking about.
That's right. The VLT, a very large telescope, and the Keck telescope, and we go and determine the redshift of that, and we've got the distance. So the dispersion, that delay in the wavelengths, tells us how much matter it's gone through, but we needed independently the distance. And that distance comes from the optical telescopes. You get a redshift for that host galaxy, so you know the distance it's gone through, you know the amount of matter it's gone through, presto, you've got the density of matter.
But that's in a direct line from the source to here. How do you then translate that to describe all the mass in the universe from the Big Bang? Well, all the baryonic matter in the universe from the Big Bang.
Well, see, this is the interesting thing. About 75%, even a little bit more, is actually located out in intergalactic space. Only about around about 15 to 20% is actually located in the galaxies themselves. The rest is intergalactic space.
That's very interesting, because it wasn't all that long ago where scientists were saying, we've found all the missing matter. It's actually ionized hydrogen within galaxy clusters themselves.
Well, this is the trouble. So there's about 20% that's in the galaxies, and there's a few tens of percent that people had been able to find in the gas in clusters of galaxies using various techniques. There's something called the Sanyev-Zeldovich effect. People had done absorption spectroscopy, so you get very bright quasars that are well behind clusters of galaxies, and you take very sensitive spectra and you look for absorption, trace species. And people are able to account for a few tens of percent of this gas. But about half of it, and it depends who you ask, because when you don't know how much is missing, you don't, when you haven't figured it out, when you haven't seen it, you don't exactly know how much is missing. But people argue it was about a half of the mass of the universe was still remaining to be discovered out in the vast regions well away from galaxies.
So this includes the voids and things like that?
Yes, right out there in the voids where the density is like it's about 2 by 10 to the minus 7 per cubic centimetre. In other words, about 2 atoms in the average office. That's the kind of density we're talking about. And when gas is at that sort of density, it's nigh impossible to detect by looking for radiation from it or even absorption as light goes through it. It's this effective dispersion that FRBs are susceptible to that is the clincher that's enabled us to see that matter. I think the problem is that people had inferred how much gas there was near galaxies, and they tried to figure out how much matter there was in the universe and account for the remaining matter. And that's kind of like looking at the tail of a dog and trying to figure out how big the dog was. If you don't have a technique that sees all the stuff, you can only guess. And that was the trouble. In fact, with some of this absorption line spectroscopy using very bright quasars to look at absorption through these things, you're looking at trace species, highly ionized species of carbon and oxygen. And so there are tiny constituent of what's there. So that's the equivalent of looking at the hair on the tail of a dog and trying to infer how big the dog is.
How much better will it be once ASCAP becomes part of the square kilometre array, once the array itself is operational?
Well, ASCAP, as you say, is but a small fraction of the potential of the full SKA. And I think the SKA will be... with its extra sensitivity, will just be a bucket for collecting these things. And you can really go to town. So whereas we have to wait in terms of, we have to share the telescope, of course, but it's particularly a month between the localisation from one to the next. But the SKA ought to be detecting these things by the bucket load every day. And that completely changes the game in what you can do. Then you'll be able to, as a routine thing, do tomography of the universe. You can make three-dimensional maps of all of this matter, because you can say, well, I have this burst at this redshift, and I have a very close, a nearby burst at a slightly different redshift, and that has a different amount of dispersion. So you can sort of build up differentially a three-dimensional map of the universe.
As more and more information comes through, we're finding that the universe may be anisotropic rather than the same in all directions. And this is the sort of tool which would really help bang that one down in a very different way to what we've been doing so far.
Yeah, it's orthogonal to a lot of other techniques. I'm not sure I believe the evidence for anisotropy in the Hubble constant, having looked at some of those papers. I suspect there's a more mundane explanation, but for those sorts of questions, these things are ideal. As I say, they're like a Swiss Army knife of the universe. They're subject to the effect of dispersion, which is the radiation's getting out of lockstep. But they're also subject to a whole bunch of other detailed propagation effects, as we call them. The Faraday rotation, which is when the linear polarization, gets rotated when it goes through a magnetized plasma. So what are the magnetic fields in the universe? And can we figure out from fast radio bursts what the magnetic field strength is in intergalactic space? That would be really interesting to know. Tough measurement, but possible in principle. Can we use them to directly measure the curvature of the universe? When we measure what's their dispersion measure, that's all that precise value is actually influenced by the curvature of the universe. And what dominates the curvature of the universe at the moment? Dark energy. And so in principle, if you had enough of these things, maybe a few thousand you'd need, you might be able to measure what's called the dark energy equation of state. So you might be able to shed light on the nature of dark energy. These are questions that the SKA might end up addressing.
And if you can shed light on the nature of dark energy, you can pretty well let us know what the ultimate fate of the universe will be.
Well, maybe. I mean, it would be lovely to know the equation of state of dark energy. It's probably a fair way away from knowing what dark energy is. And until we know actually what dark energy is, I wouldn't be so bold as to predict the ultimate fate of the universe. I'll maybe leave that for others.
Big freeze and big rips for other people.
Yeah.
That's Jean-Pierre Macquart from the Curtin University node of the International Centre for Radio Astronomy Research. And this is Spacetime. I'm Stuart Gary. Still to come, a new type of matter inside neutron stars. And China ramps up its 2020 launch schedule. All that and more still to come on Spacetime. A new study suggests that neutron stars may contain an exotic substance known as quark matter. The findings, reported in the journal Nature Physics, are based on research combining recent results from theoretical particle and nuclear physics to measurements of gravitational waves from neutron star collisions. When stars like our Sun reach the end of their lives on the main sequence, having fused most of the hydrogen in their core into helium, the balancing act between gravity crushing a star down towards its centre and the nuclear energy pushing outwards ends, and gravity wins, causing the stellar core of the star to collapse inwards. This additional mass crushing down on the core causes a dramatic increase in pressure and temperature, eventually triggering a helium flash, making it hot enough for the core to begin fusing helium into heavier elements like carbon and oxygen. At the same time, a hydrogen shell begins to burn surrounding the core, and the star's outer layers begin to expand due to the increased heat. And because it's now further away from the core, the outer surface of this envelope also cools down. This combination of expansion and cooling transforms the star into a red giant. Now, eventually, stars like our Sun fuse most of their core helium into carbon and oxygen. But they're not massive enough to fuse carbon and oxygen into heavier elements, and so the nuclear fusion process ends. Their outer gaseous envelope detaches and floats away from the star as a planetary nebula, leaving the white-hot stellar core exposed as a white dwarf, which will slowly cool over the eons. That's the fate of our Sun. But for stars far more massive than the Sun, they face a very different fate. Because they're so massive, with much higher core temperatures and pressures, they fuse hydrogen into helium through a different process, and they then go on to fuse progressively heavier and heavier elements: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, nickel, and eventually iron. But no matter how massive a star is, it's not massive enough to fuse iron into heavier elements. And so, once again, that balancing act between gravity crushing a star down towards the centre and nuclear energy pushing outwards reaches its final inevitable conclusion. And once again, gravity's the winner. Because these stars are so massive, when the star collapses down onto the core, it collapses with such power and force, it generates a supernova, an explosion so bright it can briefly outshine an entire galaxy. Now, for this to happen, the stellar core, the stellar remnant of the star, needs to be at least 1.44 solar masses. This is important because it's a figure known as the Chandrasekhar Limit, and it's a figure which means the immense gravitational collapse of the star can break through what's called electron degeneracy. That's a quantum mechanical effect arising from the Pauli exclusion principle. It prevents more than one fermion, such as an electron, from being in the same minimum energy level quantum state at the same time. But when the stellar remnant has more than 1.44 solar masses, it can punch through that electron degeneracy barrier, allowing further collapse and crushing the negatively charged electrons and positively charged protons together to form neutrons, hence the star's name, or more accurately, to form what's believed to be a neutronium fluid. Although only a couple of dozen kilometres wide, neutron stars are the densest objects in the known universe, other than black holes. They're so dense, in fact, that just a sugar cube size of neutron star material would weigh more than 100 million tonnes. Until now, astronomers have never been really sure what's going on inside a neutron star. They weren't sure if the cores of the most massive neutron stars comprise some sort of exotic fluid neutronium or something even more exotic, a state known as quark matter. Scientists now think they've got the answer, and that answer is quark matter. One of the study's authors, Associate Professor Alexis Farian from the University of Helsinki, says confirming the existence of quark matter inside the cores of neutron stars as being one of the most important goals of neutron star physics ever since this possibility was first entertained about 40 years ago. With even large-scale simulations running on the best supercomputers unable to determine the fate of nuclear matter inside neutron stars, the Finnish team proposed a new approach to the problem. They combined findings from theoretical particle and nuclear physics with astronomical measurements to try and determine the characteristics of the types of material likely to reside inside neutron stars. The authors suggest that about half the diameter of the neutron star is more likely to resemble the properties of quark matter than those of the protons, neutrons, and electrons of ordinary matter crushed down into a dense nuclear matter, the fluidy neutronium. A key factor contributing to the new findings was the emergence of two recent results in observational astrophysics: the measurement of gravitational waves from a neutron star merger and the detection of very large neutron stars with close to 2 solar masses. Back in 2017, the LIGO and Virgo observatories detected gravitational waves generated by the merging of two neutron stars to form a black hole for the first time. These observations set a rigorous upper limit for a quantity called tidal deformability, which measures the susceptibility of an orbiting star structure to the gravitational field of its companion. This result was subsequently used to derive an upper limit for the radii of colliding neutron stars, which turned out to be roughly 13 kilometers. Similarly, while the first observations of a neutron star dates back all the way to 1967, accurate mass measurements of these stars have really only been possible over the past 20 years or so. Most neutron stars have masses ranging from the Chandrasekhar limit of 1.44 solar masses up to what's known as the Tolman-Oppenheimer-Volkov limit of around 2.14 solar masses. Anything less than the Chandrasekhar limit will usually only produce a white dwarf, although there is an interval of a few tenths of a solar mass where the masses of low-mass neutron stars and high-mass white dwarfs can overlap. At the same time, anything greater than around 2.16 solar masses would overcome the strong nuclear force repulsion and neutron degeneracy pressure so that gravitational collapse would cause the stellar remnant to push through the neutron degeneracy limit, resulting in a runaway collapse, producing a stellar mass black hole. However, the smallest observed mass of a stellar mass black hole is around 5 solar masses. So, objects between 2.16 and 5 solar masses, well, we're not sure what happens there. One hypothesis suggests they produce something called a quark star. Another suggests an even more exotic type of star called an electroweak star, based on the electromagnetic and weak nuclear forces. The problem is neither quark stars nor electroweak stars have as yet been detected. In the new analysis, the Finnish team combined astrophysical observations with new theoretical results from particle and nuclear physics. This enabled deriving an accurate prediction for what's known as the equation of state for neutron star matter, which refers to the relation between its pressure and energy density. An integral component of this process was a well-known result from general relativity, which relates the equation of state to a relation between the possible values of neutron star radii and masses. Since 2017, a number of new neutron star mergers have been observed, and so the LIGO and Virgo gravitational wave detectors have quickly become an integral part of neutron star research. This rapid accumulation of new observational information is playing a key role in improving the accuracy of the new findings, and in supporting this hypothesis of the existence of exotic quark matter inside neutron stars. The authors say as more and more gravitational wave observations of neutron star mergers become available, existing uncertainties associated with the new results should continue to decrease. This is Spacetime. Still to come, China ramping up its 2020 launch schedule. And later in the science report, a new study has found that half of all people who contract COVID-19 show absolutely no symptoms of the illness. All that and more still to come on Spacetime. China's maintaining its busy launch schedule with another pair of observation satellites flown into orbit aboard Beijing's workhorse Long March 2D rocket. This latest flight from the Jiuquan Satellite Launch Center in northwestern China's Gansu province carried the Gaofen 902 and Head 4 satellites. Gaofen 902 is another optical remote sensing satellite capable of providing high-resolution images in the sub-meter class. The spacecraft, which is based on the Yaogan 2 military spy satellite, was placed in a 617 by 664 kilometer high orbit. While many of its observations will remain classified, some of its data is being made available to civilian partners in Beijing's controversial Belt and Road Initiative, as part of the CHIOS China Earth Observation System. Also aboard for the ride was the 45-kilogram Head 4 satellite, designed to monitor shipping and aircraft movements and provide Internet of Things telecommunication services. And time now to take a brief look at some of the other stories making news in science this week with a science report. It now seems around half of all people who contract COVID-19 show no symptoms of the illness. The findings are based on 2 separate studies released this week. A report in the Journal of the American Medical Association, which examined 78 COVID-19 patients, found that 42.3% were asymptomatic, showing no symptoms of COVID-19. Meanwhile, a separate study reported in the journal Thorax found that more than 8 out of 10 cruise ship passengers who tested positive for COVID-19 also showed no symptoms of the illness. A new study warns that human activity in biodiversity hotspots has now brought more than 500 vertebrate species to the very brink of extinction. The findings, reported in the Journal of the Proceedings of the National Academy of Sciences, confirms that the world is experiencing its 6th mass extinction event. And this one isn't caused by volcanoes or asteroid impacts, but by people. The researchers looked at 29,400 species on the United Nations Red List of Threatened Species, as well as information from BirdLife International, finding that 1.7%, or 515 of the species they looked at, are now on the brink of extinction. They also found that 84% of 388 terrestrial vertebrate species they looked at had fewer than 5,000 remaining individuals located in the same geographical regions as those species already on the brink of extinction, and may therefore soon be facing a similar risk due to human-driven collapse of regional biodiversity. Additional analysis suggests that terrestrial vertebrate species on the brink have now collectively lost more than 237,000 populations since 1900. And locally, the findings are even more disturbing, because they show that the Australian region has the 2nd highest number of land vertebrates on the brink of extinction, despite Australia being the smallest and one of the most least populated continents. Only South America has more species on the brink. That's mainly because of the many critically endangered frog species there. Overall, these findings underscore the urgent need for global action if we're to prevent further loss of terrestrial vertebrate species. The clock is running. Paleontologists have discovered the fossilized imprint of what's thought to be the earliest known land animal, a 3-centimetre-long millipede-like creature dating back some 425 million years to the Silurian period. Comparasabensis was uncovered on the island of Kerira in Scotland. Scientists from the University of Texas at Austin say the ancient arthropod, which was radiometrically dated, probably fed on decomposing plants. The findings suggest that bugs and plants evolved from leg-hugging communities to more complex ecosystems over a span of just 40 million years. That's much faster than previously thought. Earlier land animals dating back to the Cambrian have been detected, but they've only been known to exist indirectly because of the tracks they've left behind. Time for a bit of good news for the follically challenged. Scientists growing skin from stem cells have developed distinct layers, which are now including hair follicles. A report in the journal Nature says researchers have been able to grow skin cells in the lab for a while now, but recreating the complex multi-layered structure of skin has been a major biomedical challenge. The team were able to grow skin structure with distinct epidermis and dermis layers, as well as hair follicles and sebaceous glands, by carefully optimizing the growth conditions over 4 to 5 months. And when the near-complete skin was grafted onto mice, more than half of the grafts sprouted hair. And while those a bit thin on top might be rejoicing, the researchers say their work will also likely help scientists' understanding of genetic skin disorders and cancers, as well as one day potentially helping people with skin burns and wounds. Well, it looks like you really can use science to change the minds of people who don't trust science. A new study shows that while you'll never change the minds of those true believers, be they climate change deniers, anti-vaxxers or COVID-19 conspiracy theorists, providing scientific facts to some people who normally don't trust science will make them change their minds. However, Tim Mendham from Australian Skeptics says it only works on specific topics, not their overall fears about what they perceive as the dangers of science.
There's been a study quite recently done in the US and in Germany with a surprising feeling that if you actually give people information, they might change their mind. And looking at people who are doubtful, deniers, whatever term you want to use, of genetically modified foods and of climate change. And looking at those two areas and basically saying, can the giving of information scientifically endorsed, supported information change people's minds? And the answer is yes. It won't.
I've always thought so.
Yeah, knock it down with a feather. But at least they got the numbers anyway to show that it does happen.
I used to be very anti-GMO. I think a lot of people are like that. As the science is given to them, they change their minds, and you realise, well, it's not all Frankenstein food.
It takes a lot of effort to sort of move away from your echo chamber, right? To move away from what you believe to be true and the group you subscribe to, which sort of reinforces those views. It takes a lot of effort to say, let's find someone who says, no, that set of beliefs is rubbish. This is what the truth is, or this is what we understand it to be. And that upsets your equilibrium. It upsets your confirmation bias, where you want to believe in a certain set of things. And that wanting to believe is probably stronger than the actual appreciation of the information. One of the interesting things is that obviously with people who tend to support those concepts, climate change theory, GMO foods, etc., their minds are not going to be changed very much. They might add a little bit to it where they get a lot more information. But the people who are on the fringe, who really don't know, when they get proper scientific information and it is checked, etc., they will change their mind. Now, the interesting thing is they might change their mind about those, but they don't necessarily change their mind about trusting science. Now, a lot of people out there think science is out to get them, that it has all sorts of downsides, that therefore they worry about scientists and mad scientist sort of syndrome, if you like. But so they don't trust science to cure things. Science is unhumanized or that sort of thing. But you give them this scientific information, you don't necessarily have to say it's scientific. You give them this factual information and they will change their mind about GMO and climate change, but they won't change their mind about, do I trust science? And that's probably the most interesting.
That's really weird, isn't it? Yeah.
It is, totally. I know. They separate out the information from the process by which you come to that information. And there's a scientific establishment, as they see it, which is basically out to control their lives and make things harder for them. But at the same time, they will believe the actual facts, especially if they're presented to them in a forthright way. There are people who have said, and these researchers admit this, there are people who say that presenting scientific information is not going to help anybody. People have a mindset, they're set against it, and there's nothing you can do to change it. Well, they're saying you can, but you're not going to change the underlying problem with people just don't believe scientists or science.
That's Tim Mindham from Australian Skeptics. And that's the show for now. Spacetime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download Spacetime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favourite download podcast provider. You can help support the show and the work we do by visiting the Spacetime online shop and grabbing yourself a few goodies, or by becoming a Spacetime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more Spacetime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at Spacetime with Stuart Gary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.